So, good morning, everybody, and welcome to the latest edition of the Pangolin Seminar. Today, Gérard Besson from the Université Grenoble Alpes will be speaking to us about finiteness theorems for Gromov-Hyperbolic groups. So, over to you, Gérard.
Thank you very much. Thank you, Graham, and thank you, Andrea, for the invitation. Sometimes the connection is not completely safe, so please tell me to repeat if necessary. Maybe I put my face on the in order to be polite. Yeah, well, so I'm going to talk about some recent work of the regular guys, due to the variety of people in the audience, I decided to have a very elementary lecture, well, up to a certain point. So I will start by very elementary things and then try to explain the main ideas. Okay, so as an introduction, I want to state the main result. So in the sequel, we'll consider finitely generated groups.
Just a second, Gérard. You're not sharing your file yet.
I'm not sharing.
Yes.
It was for me, in fact, just for me. So let me share. It should be this one, yeah. Okay, do you see? Let me start again.
Now I do, yes.
You see everything. Okay, Pangolin Seminar. I'm not in my sofa. I'm in my office, but it's more or less the same. Okay, so let me start by very elementary considerations. And I want to state the main result as soon as possible. And then I spend the rest of the lecture explaining all the words which you will see in a second. So we will be considering groups, finitely generated groups, and what we call marked groups, which is just a tuple of group and a finite generating set, which we take symmetric. Symmetric just meaning that if one element is in sigma, the name of the finite generating set, then the inverse is in sigma, just for convenience. Right, and the main result is the following. So if you give yourself two numbers, delta and h, positive, non-negative, there are finitely many delta hyperbolic marked groups satisfying as the following assumption: they are non-cyclic, torsion-free, and furthermore, they have entropy less than a fixed number. And this up to isometries. It's a bit brutal to start by stating the theorem, but what I would like to do now is to explain all the words so that it becomes clear, hopefully at the end of the lecture, and so that there will be no ambiguity. The point here is that we want to count finitely generated groups with more properties. So keep this in mind, and now let's start to explain what this statement means. So the context of our work is the context of metric spaces. So it's not anymore manifolds as we were used to do in the past, but metric spaces with several good properties which make them easy to handle and more or less carrying features which resembles the case of manifolds. So we'll consider metric spaces X and D. D is the distance function, which are proper and geodesic. And let me explain what these words mean. So proper means that all closed balls are compact. A geodesic between 2 points, a geodesic is just an isometry from an interval in R into X, into the metric spaces. So it's different for those who are not familiar with metric spaces. It's very different from the case of Riemannian manifold, in which geodesic are defined by an ordinary differential equation, and they minimize only on a small distance, usually. Here we ask the geodesic to be a map which realizes the distance, so which is an isometric embedding of some interval into X, so that the distance between 2 points along the geodesic is just the difference of the parameters. We could have a more relaxed definition. This one is fine, and the space is said to be geodesic if any 2 points are joined by one geodesy. Maybe several, but at least one. And that's it. Yeah. So during this lecture, we will consider only proper geodesic spaces with more assumptions that we will see in a minute. And we will consider the action by isometries of a discrete subgroup of the isometry group on the space, so that the quotient of the space by the action of the group is compact. And furthermore, we'll need a measure, which is, in fact, we are not really dealing only with metric spaces, but what is usually called metric measure spaces. So we'll consider a measure called nu, which is gamma invariant, locally finite, and non-trivial, of course, Borel measure. And once you are given these data, then one can define one of the words that appeared in copy of XD, as usual, is given by this formula, which is looking at the volume. By volume, I mean the measure of ball of radius r around some point x. And we try to capture the logarithmic expansion, the exponential expansion of this volume of balls. And so take the logarithm, divide by the radius, and let r goes to infinity. So here I wrote lim inf. I'm sorry, so I'm doing bad thing with my, I'm not very, well, okay, so now I zoom. Okay, so now it's okay. Here we are considering lim inf of this quantity, but we are in a context where the limit exists, and the context is when at least when the quotient is compact. There are other cases in which the limit is well defined, but here we have a compact quotient. So let me close my mail because it's a nightmare. All right. Okay, so this is a very standard definition. We have been playing with that for the last 35 years. And it's very flexible in the sense that usually in a Riemannian manifold, we use the volume element, the volume measure. So there is a relationship between the radius and the volume, because they all are given by the Riemannian metric. Here we just relax this link between the two objects. And the measure is just gamma invariant and locally finite. And in fact, during this lecture, we will consider only one measure. Okay, so in the statement, one of the assumptions is that this is less than some number. So it's bounded above. So for the people who are familiar with Riemannian geometry, probably know that the volume growth of the ball of radius r is controlled somehow by the Ricci curvature, or more precisely, if the Ricci curvature is bounded below, then the entropy is bounded above. So here, in the context of metric spaces, we don't have any local invariant, local curvature. And so we replace this Ricci curvature bounded from below by entropy bounded from above, which is a much weaker condition than the previous one, as you can imagine, since by looking at the definition, everybody sees that this entropy is an asymptotic invariant, whereas the Ricci curvature is infinitesimal invariant. It's surprising that we can do anything with this notion on metric spaces, but it does give lots of information on the space. And we will try to see this later. Okay, so what I put in blue is just one of the hypotheses in the main theorem. So example of measure, the only one that we will be considering here is the counting measure. So fix a point x, and if you look at the orbit of x under the action of gamma, then just look at the sum of the Dirac mass at the orbit of x at the point gamma x. And if you make the sum, then you are just counting the point on the orbit. So because the action, the group is a discrete subgroup of the group of isometries, and the space is proper, the balls are compact, then one can check that it's really a locally finite measure, easy to check. And so it satisfies the above hypothesis. Obviously, it's invariant under the action of gamma. So the cheating here is that I call nu a measure which depends on the point, but the point takes precise every right. Okay. So it's also a very weak notion of measure, because it sees only, if you fix a point X, it sees only some kind of lattice in the space. And it's surprising that we can do something with this weak notion. Okay, so I wanted to give an example. So an example of metric spaces. This is the purpose of this slide. So I wanted to draw pictures on my tablet, but unfortunately yesterday the tablet became not compatible anymore with my computer. So I did something else, and I hope it's going to be fine. So if one considers a finitely generated group and a symmetric finite generating set, as we have been doing so far, then one can define a graph, which is called the Cayley graph. And I guess it's a notion that almost everybody is familiar with, but let me recall with words what it means. You start by taking a vertex at the identity element, and then you draw edges for each element of sigma and of sigma. So any gamma which is in sigma give rise to an edge, and gamma minus 1 to somehow the opposite edge. And you keep doing this every time you multiply an element of a group by an element of the generating set, then you draw an edge from the first element to the second. And so one gets a graph here, which is called the Cayley graph, and denoted, as you can see, by G curl gamma sigma. And this can be endowed with a metric. So usually we consider the word length metric, which is exactly the number. If you take two element gamma and gamma prime in the group, the distance which is given by this finitely generated by this finite generating set, distance sigma of gamma to gamma prime, consists in the following. You consider gamma minus 1 gamma prime, and you write this as a product of element of sigma, which is exactly what a finite generating set is for. And you count the number of elements in this product, and you try to write it with as little element as possible. And when you get the smallest way of writing this product as a product of element of sigma, then you count them, and you get an integer which is called the word length of gamma minus 1 sigma prime. And so with this distance, the distance between the length of an edge is the distance between two successive vertices related by one edge is 1. And so we can turn X into a graph, a metric graph with edges of length 1. And this is one of the interesting points. And by construction, and I don't need to give more details, the group acts by isometrism on this graph endowed with this word length distance. So this is really by construction, and this is a quite trivial remark. But we are in the situation where we have metric spaces. In fact, it's a graph which is locally finite, so it is proper, and with a group acting by isometrism on it, the group itself. And if you mod out by the group, I mean, what you get is a bunch of circles, a bouquet of circles, and each circle corresponding to one element in sigma. So the quotient is compact and the diameter is 1. So we are really in the situation that we are trying to study. So this we should keep in mind, and at the very end, well, not at the very end, close to the end, it will come back into the story, but it's a very good example. So I plan to draw pictures directly on the slides, as I've seen, we usually do, but I'm sorry I couldn't. So on the next slide, there will be a picture, which I drew yesterday night. So the counting measure makes sense here. You have a Dirac mass on each vertex, and then you can count, if you take a ball of radius r, the number of elements in this ball. Okay, so a definition. So there is another word which appear in the main statement, which I will be defining now. So if you have two marked groups, so group with a finite generating set, symmetric, then we say that an isomorphism between the two groups is an isomorphism of marked groups if phi of sigma is equal to sigma prime, which is a natural definition. And it turns out that, I'm sorry, hope you see well that the slides, I mean, it's not in full screen because Graham told me not to use full screen. It turns out that it is obvious that if you take an isomorphism of marked groups, then it gives rise, and it is equivalent to an isometry between the two metric space obtained as Cayley graph of the two groups. And in the main statement, there was at the end of the sentence, there are finitely many blah 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 up to isometries, and it means exactly this. So I will be confusing isomorphism and isometries every time I will be considering these marked groups here. So I just wanted to fix this notation. Notice that the graph really depends on the symmetric finite generating set. So that's why it is associated to a marked group and not to a group itself. So one has to be careful with this. And of course, now we have this and we can define an entropy. First, a picture. So this is for a free group. So this is a classical picture. Yeah, so you see the distance is D and AB, and on the picture is called alpha and beta. It's my passion for Greens that pushed me to use Greek letters, but in fact it's A and B. So this is a standard way of representing the graph of a free group in two generators, as usual. And the quotient is just a bouquet of two circles, one corresponding to the element alpha or A, whatever you call it, and the second one to B. So it's the most elementary example. Right. Okay. And yeah. Okay. So what I wanted to say about the entropy will come later. So now I come to the second point. So the main issue in this lecture is to count groups. So how do you count group? So let's consider a finitely presented group. So it's the first finitely generated group. You may be, so I was naive at the beginning and think that if you can bound the number of elements in a generating set, then you can bound the number of groups, but it's obviously not true. Even if you consider groups with a generating set with two elements, there are infinitely many of them. So you have to add one piece more, one piece of data, and the piece of data concerns the relations in the group, as it is obvious. So finitely presented group is a finitely generated group with a subgroup of relation, which is finitely generated as a normal subgroup by some R, which is a sequence, which is a finite family of elements in gamma. So what does it mean finitely generated as a normal subgroup? It means just the following: every relations in the group is the product of conjugate of the relation of the basic relation in R. So you have a finite set of relations such that if you conjugate them and make all the possible product, you get all the relations in the group. Okay, so now with these two data, then one can show a very elementary proposition, just a counting. So if you give yourself two numbers greater than one is greater than 3, doesn't matter, just to avoid trivial example. There are finite, there is, I'm sorry, I missed the word, there is a finite number of marked groups such that the generating set has a cardinality bounded by capital N, and the word length of a base for generating the relations is bounded above by the number P. So In other words, so generating set is the bounded number of elements is easy to understand. And in other words, any relations in the group is a product of conjugates of elements in R, which are in finite number of them, which is finite. And furthermore, these elements in R have word length, which is bounded above. So they are themselves product of element in sigma, but not more than P. And then it's quite easy to show that this proposition is really trivial. I mean, it's really easy. It's a nice exercise to do. So it's quite easy to show that then the number of such group is bounded above, and we try to give the number. Just forget about the precise value of the number. It's just a bounded number of groups which satisfy these two properties. So they are more or less up to a finite number characterized by sigma and R. Okay, so we want to bound the number of groups here with some properties. So we have to control the size of a generating set, and we have to control the word length of the relations. And in full generality, it's not that easy. But here we have extra assumption, which I will detail in a minute. So the goal is clear now. We have to estimate cardinality of sigma and bound the size of the relations in R. I should have said. So there is a core of the relation. I don't want to call it a generating set of the relation because it generates the relation up to conjugacy. But there is a core which is made of relations with a small size. Right. So let's move further. So now I come to the definition of hyperbolic. So one word that appeared is hyperbolic, spaces and group. Most probably 90% of you people know what it means, but let me give a definition anyway. So we consider a proper geodesic metric space, and it is said to be delta hyperbolic if all triangles are delta thin. This is a very nice definition, except that I will not define delta thin, and it's defined in this picture, which is a standard picture that you find on the internet and which have been stolen on the internet, of course. Because I've tried to draw myself a picture like this, and it was a nightmare. Well, anyway, what does it mean? It means that you consider a triangle, and you have to consider any triangle, then a point on one edge of the triangle is at distance less than delta, at distance less than delta of the union of the two other edges. So that the triangle looks like the red triangle on the picture. Namely, it is thin in the center. It looks like a negatively curved triangle. So notice that you should consider any triangle, and in particular, if you take 3 points, there might be several triangles between these, based on these 3 points, because there might be several geodesics between any 2 points. And so if for any triangle you have this property, then the group, the space is said to be delta hyperbolic. As you can guess easily, so think to a Riemannian manifold, since the space is proper, that is, the small balls are compact, for the small triangles, you will always, by compactness, find some delta. So this constraint, which is a curvature-like condition, doesn't say anything about the local geometry or topology. So again, it's some kind of asymptotic constraint in the sense, not really asymptotic because it considers triangles which are big enough. So it gives some information on large scale geometry of this space. Okay, so this delta can interpret it as a negative curvature. So I gave here the interpretation. So assume that we are in a negatively curved or non-negatively curved space. So the curvature is negative. So the delta, which is a distance, satisfies this kind of heuristic equivalence. The delta square behaves like the inverse of the curvature. Right, and so this number can be computed in very few cases, and I think of course, it's computed for the real hyperbolic space. And to be honest, I don't know for the complex hyperbolic space. It's not clear to me, but it should be, well, it's not clear. What you can see with this equivalence here, which is just a heuristic, is that if the curvature goes to 0, so if you come to the flat space, then delta goes to infinity. And of course, you know that if you draw a triangle on R2, then this property is never satisfied for any finite delta. So somehow delta is infinite. On the other hand, at the exact opposite of this, if you consider a tree, right, a metric tree, locally finite, then delta is equal to 0. Right, so the whole range of delta correspond to somehow a condition like, so in our, in the main statement, delta appears. So if delta is away from infinity, it means that the curvature is negative and away from 0. So somehow it's an upper bound of the curvature, giving oneself this delta. And the upper bound on the entropy, I said it was a lower bound on the Ricci curvature. So we're working with two curvature bounds, but which are not really curvatures. Not infinitesimal, but one is asymptotic and the other one is related to the large scale geometry. Right, I'm very slow, but it doesn't matter. Okay, this I already said. Does give about local geometry, and this I already said also. Okay, and there is something else. So, okay. Now, the definition is that a group, a Mark group, is said to be delta hyperbolic if the Kelly graph is delta hyperbolic. So it allows to give a definition of an hyperbolic group. And in fact, a group is said to be hyperbolic if there exists sigma, so that gamma sigma is delta hyperbolic. So one cannot say that a group is delta hyperbolic. This delta doesn't mean anything as long as you don't not chosen a finite generating set. All right, so this is just a quick scratch not course, but scratch account of delta hyperbolicity. And of course, the number delta depends on sigma also. Right. So now there is a proposition which is very interesting for our purpose. And the proposition is this one. If you are given a Mark group, which is delta hyperbolic, that is the Kelly graph associated is delta hyperbolic as a metric space, for any sigma which satisfies this property, you can choose a finite number of relations which gives a presentation of the group, and this relation of word length which is bounded above, and it is even more precise, is bounded above by 4 delta plus 6. So this is what is miraculous with the hyperbolic group, is that this part that we have to control, the word length of the core of the relations, is given just by easy consideration. So it's an easy exercise. I will explain something later which is more or less the same. But if you want to look at this, you should look at the wonderful book by Brighton and Effliger, and in section, well, in chapter 3, section gamma, there is a proposition which shows this in a couple of lines. So it's not very difficult to show, and I don't want to spend time to explain it, but it's remarkable. So now we have this corollary that if we can bound the number of generators, if we can choose sigma so that the number of elements of sigma is bounded, then because of this remark, we have bound, so there is a finite number of delta hyperbolic Mark group with a cardinality of sigma less than some k. So the only issue to control this, to prove the main theorem, which is a finiteness theorem, is to control this finite number of, is to control the generating set. And geometrically, because we want the entropy to be involved and the delta also. All right. So the goal is clear: is to estimate the cardinality of sigma, and in terms of h as possible, the entropy. And this, if you remember the definition of this Kelly graph, these sigmas, they belong to the ball of radius 1 around the identity element. And you want to, and the number of elements is some kind of volume of this ball in this setup. And we want to control it in terms of some asymptotic invariant. So it's absolutely not natural. And again, it's not clear that one can do that. But I explain how to do it. It's a bit, I have to speed up. Anyway, so now we come to this story. Geometric generating set. How can we geometrically control the number of generating sets, of elements of a generating set? So this is a story which goes back to before Jean-Pierre Serre, and certainly Gromov did it. But I mean, this classical proposition in the book by Serre on trees, the idea that Gromov described in the so-called Green Book was already here, and Serre tells that it's not coming from him, and he gives the name of the people who have contributed, like Malbif and Gerstenhaber, and these people specialists in group theory. And so the statement is the following. So the group acts by isometry. So acting properly means just that gamma is discrete in the isometry group of XD. And XD is a path-connected space, so just don't need to have a geodesic space with a compact quotient, with diameter bounded. Then this space, which is then this sigma, which is the number of element of gamma. So I put gamma star because I don't want to include in a generating set the identity, but it doesn't matter when you want to count the number of elements. So you look at the number of element of gamma, whose displacement at x is less than twice the diameter. Then it's symmetric, obviously, by construction, and it's a generating set, which is the purpose of this proposition. Right. And so we get a geometric way. So it looks like a ball of radius 2D around X. So again, we want to control some kind of volume of this ball of radius 2D around some point. Okay, so this is a very easy to prove. And let me go quickly through the proof. If you take an element gamma in capital gamma, and you look at the path from X to gamma X, and you subdivide the path. So a geodesic, well, no, a path. We don't need geodesic here. Subdivide the path in points whose distance between two consecutive points is less than some epsilon for epsilon positive. Now, when you look at, so the points are called xi, and when you look at xi, then because in the quotient, it's in the quotient, and the quotient has a diameter less than d, there is a point of the orbit of x, which is a distance less than d. So gamma I x is the point of the orbit of x. And then you just write gamma as a product of elements, which are sigma, which I call here sigma I, and sigma I are just gamma I minus 1 to the minus 1 times gamma I. It's really easy to check that sigma I belongs to the space here, sigma 2D plus epsilon. So I took this epsilon because I want to work with open balls, and in the definition of sigma, it's closed. And then you just let epsilon, sorry. Then you just let, just make the remark that because of discreteness or properness, whatever you call it, there are finitely many elements of the orbit of X in any ball. So if epsilon is small enough, then the open ball sigma 2D plus epsilon is the same than sigma 2D of X. Right. So you see, the proof is very easy. And in fact, the proof in the case of delta hyperbolic group, where we find this 4 delta plus 6 is as easy than that, where we add an extra data, which is this property of triangles. But it's not more difficult than that. So you can check in the book by Besson and Lufliger. Right. So now we know. So this proposition is very classical. Right. So let me come to the main result. So the main result is the one that I stated at the beginning, but it relies on this theorem. if you are given three numbers, so delta HD, and a subgroup of the isometric group, which is discrete. I did not write it here, I'm sorry. As before, it should be discrete, non-cyclic, and torsion-free to avoid stupid things. We'll come back to this later. If the space is delta hyperbolic, and if the quotient is compact, so it is finite diameter, so bounded by delta, and the entropy of X is bounded above by H, then for every X, the symmetric, generating set that we have been defining before, which is called sigma 10 times d plus delta at X. I see that I made a mistake here with X, as a cardinality that which can estimate just in terms of delta H and D. And that solves the problem because, as we said, we have the control on the relation, on the core of the relation, and now we have the controls on the generating, on the size of the generating set. So again, I'll say it in a few minutes. This sigma underscore R should be understood as a ball. So we are controlling here some kind of ball around X for a measure which is a counting measure, actually, really a ball, the measure of this ball, in terms of some asymptotic invariance, H, and to a lesser extent, delta. Right, and this is the point, main point. Right, so for counting the hyperbolic mark group, we just apply this to where X is the Cayley graph. So diameter of the quotient is 1, as I said before, and that's it. And we get and the entropy is the one that I didn't I defined for any metric space. Right. So this is straightforward after to apply to the group, and yeah. Right. So the finiteness comes from this remark. We are happy that we have been helped by this elementary but still very important remark that anytime you have a group which is delta hyperbolic with some finite generating set, then you can choose a core of the relations which for which each relation in this core has word length less than some given number, depending only on delta. It's an amazing fact. Right. So there are two interesting tools to prove this theorem, and my goal at this very end is to explain these tools. And so let's start with the first one. So here, so I forgot the X in this generating set. The generating set is just the counting measure of a closed ball because in the definition of this sigma underscore 10 times d plus delta, there was related to distance less than or equal. And the balls that we are considering usually are open, which is a minor drawback. So we are just counting the number of orbit point in this ball, orbit point of X in this ball. And to count them, we have the measure, which is the orbital measure or whatever you call it, the counting measure. Usually we use this term. And so we are calculating some kind of volume of this ball, right? And how do we really relate the volume of this ball to the entropy, which is an asymptotic object? And this is the purpose of the next theorem. So this is something which has already been published, and it looks very frightening at first glance, and even to me. I mean, I'm used to it, but it frightens me. But we should not be frightened. And so let's go through the statement. We take XD to be a delta hyperbolic metric space. As before, gamma is a discrete subgroup of the isometric group of XD and compact quotient with a diameter bounded by capital D and entropy is bounded by H. Then, for any point and any couple of numbers, small r and capital R, well, I should not use capital. I should not have used capital R because it meant relations, but I will change them after this lecture, which are big enough, and the big enough can be made precise, explicit. So 10 times d plus delta. Then the ratio of the measure of these two balls is bounded above. So what does it mean? So think as mu as being a volume. So the volume of the ball of radius capital R divided by the volume of balls of radius small r is bounded above. This should remind you of Bishop-Gromov inequality. So Bishop-Gromov inequality is an improvement of Bishop inequality made by Gromov, which is a small remark in his green book, but very interesting, which says that Bishop inequality tells that if you have an information on Ricci curvature, then the volume of balls is bounded above by some comparison space, by the volume of balls in some comparison space. And Bishop-Gromov concerns ratio of volume of ball. Right. The striking point is that if you are familiar with Riemannian geometry, Bishop-Gromov inequality is very useful when the curvature is positive, non-negative, I should say. Whereas here we are in a context with our assumption, a context that curvature is rather negative, and delta hyperbolicity, of course, corresponds to somehow some negative curvature. But it works pretty well. And to be honest, we don't know how to do it when the curvature when the space is cat zero, for example. We don't know yet how to do it when the space is cat zero. But we are working on that. Nevertheless, with delta hyperbolic space, it's fine. And we get this upper bound. So here you see the ratio between capital R and small r, which is normal. It should be dimensionless. The 3 and the 25/4 you should forget, and the 6 also. They are just numbers that we computed just to show that we know how to compute, and we know that explicit numbers are important. And there is this exponential 6h. The 6, as I said, is irrelevant. HR. So again, h as the dimension of the inverse of a distance. R is a distance, so this is dimensionless, and this is the right rate of growth somehow. So if h becomes very big, meaning that the Ricci curvature somehow becomes very negative, then this grows quickly. Right. So the proof of this is quite involved, and I will not be able during the last minute to give even any hint because it's so we posted a paper with lots of pages. Well, not only on this, but the proof of this is very involved. But it's striking that we have Bishop-Gromov inequality in this context. Sorry. So how can I get rid of this stuff? Anyway, it's not true. As I said, it's not true for small radii, but it's normal because this delta hyperbolic space, the delta hyperbolicity doesn't say anything on small scale. So we should not have a result on small scale, and we don't have. If we want to have a result on the small scale, we should add some more hypotheses, and we have results where, but I didn't want to add more hypotheses here. For me, it's satisfying like this. And Bishop-Gromov type inequality, which I already said. So I will finish by I will try to explain there is another big theorem that we use in the proof. There is another result that we use in the proof, which is not a result of ours, which I want to emphasize because it's really beautiful. I should say also, but I don't want to compare the two. And so let me start by trying to do the proof. Let's try to do the proof. So we for the sake of simplicity, I set R equal 10 times D plus delta. And what I call A is the set sigma R of X. And I recall that this is just the set of element in gamma, well, gamma star, so that the distance between X and gamma X is less than or equal to capital R. And I define A times A as being the product of elements, of, the set of products of elements of A. So you take one element in A and another element in A, you make the product, you look at all possible products, and you create product of A by itself. So it's not difficult to see that it is, well, we make products of elements which are in ball of radius R. So it's not difficult that the product falls in balls of radius 2R. And here again, there is this issue because the balls that I'm using are open balls, and the sigma was defined with less than or equal. So I had this epsilon, but it's completely irrelevant, just to make sure that I'm writing correct things. Right. Okay, what do we do with that? Then we use our Bishop-Gromov inequality to control the ratio between the cardinality of A times A and the cardinality of A. And somehow we are looking at some kind of doubling property. When you make this product, you double the set A for somehow. And in fact, ratio between these two cardinalities. With the help of our measure, it can be written as this. So here, balls are open, and that's why in the denominator, it's smaller than cardinality of capital A. So I see there is a question. No, someone is leaving. Andrea, okay. So it's no question. All right. So we have this inequality for free. And of course, our Bishop-Gromov inequality gives us an upper bound of this in terms of capital R, H, and epsilon. In fact, I want to retain from, so here the radii are 2R and R. So you remember, let's go back to see if I can. Yeah, so this capital R divided by small r will be a number 2. So let's forget about it. So the only thing that is left is this exponential of HR. All right, so we get in fact a number depending on R times H, and this epsilon, which we will let go to 0 right now. Okay, and R is 10 times d plus delta, so let me retain d plus delta, and the 10 is included in n. Okay, so we have a control of this doubling, and why is it good for? What is it good for? So the second tool is this beautiful theorem by Brouillard, Green, and Tao. And I wanted it to be completely correctly written, so it's big, long. I'm sorry, but I spent some time reading it with you. So you given a number k, and there exists universal constants, nu of k and nu prime of k, which are not 0, integers. So just because of this number k, with the following properties. Now you take a group J, and if A and B are finite non-empty subsets of capital J, such that the cardinality of the product is less than k times the product of the cardinality to the right power to have a consistent thing, then the group is somehow, then it means that the growth somehow is the doubling property is controlled. And for those who are familiar, the group should be simple, like nilpotent or something like this. So it's not the case, but the theorem says the following: then there exists a subgroup G0 of G and a finite normal subgroup N0 of G0 such that A is covered by at most nu of K, left translates of G0. So A is just a set, but you are looking at left translates of this group and you can cover this set K. And the property of this G0 is that up to a finite subgroup, it is nilpotent. And furthermore, it admits a generating set, which we can control, but this you can forget. So let's forget about N0. Then you can, if one has this kind of control, then you can cover the set A by a number which is known or bounded above of left translate of nilpotent group, which are simple groups compared to delta hyperbolic. So if you are familiar with Margulis lemma, this is a really beautiful version of Margulis lemma. And they have other results in the same vein, which are really very nice. Right. Okay, so now we can combine both. I'm sorry. So in our case, N0, well, okay, in the case of delta hyperbolic space, which are torsion-free, there is no finite normal subgroup, because then that would induce some torsion. So in fact, it's really the case where we have this nilpotent group, which such that the translate covers the set A. Right. Okay. So I give the final argument, and then I will have to stop. And so let's do this. So we take for K this N that we have been computing before, and now we apply this beautiful result by Breuer, Green, and Tao. And so there are elements in gamma, well, in a subgroup G0 of gamma, gamma 1, gamma nu of K. So this nu of K is a bound for the number of such elements, so that, as you can see on the right-hand side, the translate of G0 by this element gamma I completely covers, so the intersection of the translate with sigma 10 times d plus delta is equal to 10 times d plus delta. It's easy to check that these translate, they are either disjoint or identical. So we can take a subset of S or S itself such that they are all different and they don't intersect. Right, so you can cover this ball by a left translate of nilpotent group. It's not difficult to check either that you can choose gamma I belonging to sigma d 10 times d plus delta. Right, but this equation above is interesting. Now there is a point we are working with delta hyperbolic group, which are torsion free. And so in this context, nilpotent means cyclic. So J0 is nilpotent, so it should be cyclic. And in fact, it should be Z. So in fact, G0 is just one element and all the powers of this element. Right, as it is written here. So the translate are just elements of this type. Right? And so if we want to compute the number of elements in sigma d times d plus delta, we will compute the number of elements in sigma d times d plus delta intersected with gamma I G0, and we get a number which you can multiply by nu of K, and we get a number finally, right? So we just have to compute this one and we get the answer. Right, so let's look a little bit carefully. So yeah, the first sentence is obvious because all the elements in gamma G0, yeah, so I should add, yeah, well, okay, so this is first inequality is a restatement of this intersection. You look at element in gamma G0, which are distance less than 10 times d plus delta from X. And because gamma I belongs to this sigma 10 times d plus delta, we can choose it in this way. Then it's not difficult to check that this implies that d of X to sigma k of X is less than 20 times d plus delta. Yeah, of course, it's just a triangle inequality. So we just, you see, we have this sigma, which we don't know. And we want to compute the number of K. We want to give an upper bound of the number of K such that this inequality is satisfied. And of course, you can feel the difficulty now. If sigma is very small, if the displacement at sigma is very small, then there will be lots of K. But let me go further and we come to this point. So this cardinality is the cardinality of K such that K times L of sigma is less than 20 d plus delta. And L of sigma is defined here. How can I get rid of this stuff? Well, anyway, it will disappear. L of sigma is just the asymptotic displacement of sigma. So it's just a limit of distance of X to sigma n of X divided by n. So just some kind of asymptotic displacement at X. And this does not depend on X, and this limit exists because it's easy to check that the sequence distance of X, sigma n of X, is subadditive. Right. So this number is less than K times absolute value of k times L of sigma, number of k such absolute value times absolute value of k times L of sigma is less than 20 d plus delta. And of course, so you have the positive k, the negative k, so 20 becomes 40 d plus delta divided by L of sigma, and the 1 comes from k equal to 0. So these three lines are straightforward. But included in this three line, there is the use of the Bishop-Gromov inequality and the Breuer-Green-Tao result to reduce the computation to the computation of this gamma I G0, and this G0 are nilpotent, which in this case mean cyclic, mean Z. And we know that sigma D times D plus delta by Breuer-Green-Tao is covered by a number of translates which is boundable. So the combination of all these gives this result. And here we are stuck because this L of sigma could be very small. So we need an extra result which we proved. And I will end with this because it's a bit too much, but let me state the result. And please don't look at the numbers, just the flavor of it, right? So we are always in the same situation, and you take an element in gamma, which is not the identity, and not torsion-free, then the asymptotic distance is bounded from below. And we can show that here. So nu is the function that you saw before in a previous slide, and it's bounded from below by this number, essentially d, delta, and h somehow. So strangely enough, the proof of this is a little bit more involved than the previous one, but it relies on the same ideas. We have to use our Bishop-Gromov, and we have to use also Breuer-Green-Tao. It's a bit more involved than the one that I sketched, and it will take a lot of time to explain the details. But it's some kind of, it's not a systole, but you can interpret this as a closed geodesic for which you control the size somehow. So if you look at all this space with the property that we are considering here, then you cannot have closed, I'm exaggerating. It's not a closed geodesic, but let's think like this, heuristically. You cannot have very small closed geodesic. So you control somehow from below. The technique is exactly the same than before. A little bit more tricky, but the trickiness, I don't know if this word exists in English, relies only on technical issues. And you don't want to see this. And then now, if we come back to the previous slide, this and the proof, because we have a low bound of L of sigma, and that gives an upper bound of this expression, and so an upper bound of this, and the main proposition applied. So this finiteness theorem, which I presented in the case of a group, in fact applies to group acting on spaces, as you can see. In fact, I use the group acting on spaces, and not only on the Cayley graph. So it applies to lots of situations, and in fact we have several finiteness theorems, group acting on delta hyperbolic spaces, up to so finiteness up to isomorphism, and finiteness up to quasi-isometries. And also this induces some topological finiteness, which I don't want to describe. But here you have the main ingredient, which are these two towers. I should not say that. We have the main ingredient, which are these two theorems, the Bishop-Gromov on the one hand, and the Breuer-Green-Tao on the other hand. Breuer-Green-Tao is related to some kind of Margulis lemma, and the Bishop-Gromov is related to Bishop-Gromov. So nu is not a, I'm sorry. So yeah, there is a question. I've messed around the notation, so please accept my apologies. Nu here is not a measure. So nu is the function. So I should not use the same notation for two different objects. And here there is a function of a number k, and this is also called nu of k. And I should have been careful with that. At the beginning, nu was a measure, but then I used nu x gamma for the measure. Now nu here is not a measure anymore. I'm sorry, there are two misleading notations, the capital R and this one here. Does that answer your question? I'm really sorry. Next talk will be better because I will correct this stupid and misleading notation. All right, so the paper is not ready yet. It will be ready soon and will be posted. So I thank you very much for your patience.
Okay, so let's please unmute our microphones, and thanks, Gérard, for this talk.
So where are you? I don't see any face. Okay. Thank you very much. I don't see anybody. Ah, yes, I don't see anybody because. Okay, sorry. Okay, so now I see everybody. Thanks.
Thanks, Gérard. It was a great talk. Maybe I've heard some question in the background. Someone was speaking. Or anyway, if anyone has questions. By the way, yeah.
I have a question. Yes. Hello, Gérard.
Hello.
Hello. Do you have some idea of what happens if you admit also torsion?
We have counterexample. We have example which shows that all the hypotheses are necessary. So we have example showing that if you allow torsion, then it's not true anymore. The finiteness is not true.
Okay, thank you.
I don't remember. I'm sorry, I don't remember the example right now, but it's written in our papers. We have example showing that all hypotheses are really necessary here.
Okay.
If I could think half an hour, I would come back with the example, but I would send it to you very soon.
So Graham had to leave a few minutes ago. It's the first time that Graham misses any minute of this seminar since the beginning.
Yeah, he told me that.
But he sent me some questions. So Graham has this question.
Too bad. He should have left without questions.
Graham is wondering, based on your main theorem, and on the fact that a lower bound of the Ricci curvature implies an upper bound of the entropy, it seems that one can deduce that there is only a finite number of hyperbolic manifolds of a given dimension larger than 3. Can you explain that? I'm puzzled. It's not true, right? Yeah, but why? What's wrong with this argument?
You need
so there is. So first of all, there is this diameter bound that you have to consider.
In your first slide.
Okay, let's go to the first slide. First slide concerns groups, right?
Yeah.
Okay, let's go back.
So the idea is let's count the fundamental groups of hyperbolic manifolds of given dimension, which determines the manifold.
Yeah, but for the generating set, you need the bound of the diameter, no? To control the entropy.
Yeah, but
to have a relationship between the discrete entropy and the entropy that is given by n-1, then you need the generating set. So you need the bound on the diameter. This is a trick, I think.
Yeah. So this is a point. I mean, here we have a generating set whose entropy is bounded. But now, how do you choose your generating set when you look at the fundamental group of a hyperbolic group? Then you have to have a bound on the diameter. Okay. And so Misha knows this much better than me, so he can tell.
So yeah, basically the answer is the lower bound on the Ricci curvature gives an upper bound on the entropy, but this upper bound on entropy does not only depend on the lower bound of Ricci, it depends also on something else like the number.
Yeah. So in that case, I mean, for groups, it depends on the generating set.
Yeah. And the other Graham's question was if any bound on scalar curvature implies.
I don't know what scalar curvature is. And unfortunately, so this is a good question, of course, but so there are all these synthetic version of Ricci curvature and so on and so forth. Here we have a very weak version of the curvature with this asymptotic notion, but I don't know about such a notion for scalar curvature. Let me see. No, even in small dimension. I don't know. I don't know. And in fact, there is a question that was asked by Gromov long time ago. in 1982. And the question is that it's a stupid remark. If you look at, I'm not stupid, I should not say so because, well, he's not listening, right? The remark is that if you look at Riemannian manifold and you look at the volume of small balls, then the volume is more or less driven, at least at the second order, by the scalar curvature. And if you look at the volume of big balls, then it's driven by the Ricci curvature and by the entropy. And in between, we don't know anything. So this volume growth, this volume function is very complicated to understand. And he told me that again last year when I explained this work. And he said this volume function are very difficult to understand. And he, in this paper in 1982, he explains that he was struggling trying to get some information in some special cases. So the scalar curvature is really a problem now. Yeah.
Does anyone else have questions? If not, I have a silly question.
Silly. Come to my office and tell me.
That's a very one. So if you fix one group and you change a generating set, how does the entropy change from one generating set to another?
If you want a precise answer, I don't know. And I must say I don't know. I don't know. Well, if to. Yeah, okay. So if you take a hyperbolic metric space, which is delta hyperbolic, and which is quasi-isometric to another metric space, you can compute the delta hyperbolicity constant of the hyperbolicity constant of the other space. Now, if you change the generating set, then you have quasi-isometry isometric graphs, right? Cayley graphs. Mm-hmm. So if you can find the quasi-isometry, the constant in the quasi-isometry, you can compute the delta prime of the hyperbolicity of the other graph. I don't know a formula to tell you here. You really need the constant of the quasi-isometries.
So the reason why I'm asking this question is the following: if we want to count marked hyperbolic groups only up to quasi-isometries instead of up to isometries, is there a chance to have finiteness with only an upper bound on the entropy and no bound on delta?
So we have a result like that. So let me see, but it's recent, so I don't remember the details. What do you see right now? You see still the slides, or?
I still see the same slide. Yeah.
Okay, you keep looking at the slide, and I will try to find the paper, the paper which is being done. So we have a result for with quasi isometries. So where is it? Sorry, but it's for group acting. It's for. Yeah, okay. I see the examples on the torsion-free example. Okay, so we have the answer to the previous question. So I'm sorry, let me go back. Yeah, to the statement. I'm lost in this paper completely. Yeah. Okay. Okay. So if you look at the space, so here is the result that we can prove. You look at the space of delta hyperbolic spaces with entropy bounded above by H, which admit the action of non-cyclic torsion-free group, discrete, of course, so the diameter quotient is bounded above. Then this space has finite as cardinality bounded above by some number which we can compute up to precise quasi-isometries, 5/4, 25/2D, and D. So the constant of the quasi-isometries are precisely computed. So this should apply to group, actually.
Yeah, okay.
Yeah, this of course applies to groups.
But I'm confused, but this seems to me weaker than than your main result, right? I'm confused, sorry.
No, now I'm puzzled by your remark, and okay, I have to think a little bit more. This is for, I have to think a little bit more.
Well, I mean, of course, it's more general in the sense that it's just for an action on the hyperbolic space. It's not just for a group.
Yeah.
But if you restrict to groups,
so I have to think. I have to think a bit more. This is brand new. We did it a week ago or two.
Yeah, my question was basically if you can get rid of dependence on delta.
But I think we can get a similar result with the quasi-isometry.
Okay. Up to arbitrary quasi-isometry, maybe.
Up to arbitrary quasi-isometry.
Okay, thanks. Are there other questions? Yeah, indeed, Nicola, thanks for the remark. It's what I just said here.
Okay, so where are you? I'm trying to find the slides are. I'm lost on my computer. Does it happen to anybody else to be lost on his computer? Yeah, okay, I don't find the slide anymore.
No, but it's fine, don't worry.
Okay, anyway. So
go ahead, Gérard.
It's not wiki, yeah, it's not wiki for general space, but for groups, yeah.
Yeah, exactly. Okay, if there's no other question, let's thank Gérard again for this excellent talk.
Thank you very much.
Merci, Gérard.
So contrary to what Graham said, I mean, I prefer to travel than stay in my office and give lecture.
We too.
I wish I could go to Brazil anyway. So
we won't take Graham.
Thanks a lot. I'm sorry for being tired. Bye bye. Thanks a lot.
Bye guys. Thanks.
Bye guys.